All right, section 8.5, partial fractions. This is a really neat technique we're going to use. We've learned way back in elementary school how to add fractions and get a common denominator and make one fraction. In Algebra 2 we did it with letters, but we've never learned how to go backwards. And so what we're going to do here is we're going to take the function 3x squared plus 7x minus 2 over x cubed minus x squared minus 2x and break it into different fractions to see what they started out to be before we added them together. So the first thing you do is you factor the denominator. And I'm actually going to do this problem two different ways. The way that's in the book, which works every time, and then another method which it's called the finger method. It's going to be kind of hard to explain when I'm doing this without being able to show you something, but we'll give it a shot. Okay, it's not quite factored yet. So 3x squared plus 7x minus 2, and then an x plus 1, and an x minus 2. So that means that there could be three fractions, one that has a denominator of x, one that has a denominator of x plus 1, and one that has a denominator of x plus 2. And we're going to, on the top, we're just going to write some numbers, a, b, and c. Now what you do is you multiply both sides of the equation by the common denominator. This is the method that's in the book. So of course on the left side you're just going to get the 3x squared plus 7x minus 2. But on the right side the x will cancel and we get a times x plus 1 times x minus 2. And then the x plus 1 will cancel for the second fraction, so I get an x and an x minus 2. Third fraction, the x plus, should be a minus 2. Sorry. Minus 2 is going to cancel, and I get left with an x and an x plus 1. That would have made a mess. Then we continue by distributing and multiplying everything out. And we get ax squared, let's see, a negative 2x and a 1x is a negative x, a negative ax minus 2a plus bx squared minus 2bx, and then plus cx squared plus cx. Now group all your x squares together. And I'm going to take the x squared out. All of the x squares, oh, I don't want to write it in that order. I'm going to take all of the x squares and factor out the x squared. Then I'm going to take all of the x's. The x's would be a negative a negative 2b, and a c, x's. And then my constants would be the 2, just the 2a. Minus the 2a. Okay, now, looking at this first piece, the x squares, if the left side has to equal the right side, then the a plus b plus c in front of the x squared must equal the 3 that's in front of the x squared on the left side. So I can write this equation, taking the coefficients in front of the square terms. Then the x's, this piece over here, the negative a minus 2b plus c must be equal to the coefficient in front of the x on the left side, which was a 7. And then finally, the 2a, the negative 2a on the right-hand side must be equal to negative 2, and that one I can solve. So a is 1. Now I'm going to go back up to the other two equations and put the 1 in there. Minus 2b plus c is 7. I'm getting my constants all on the right-hand side. This would turn into b plus c equals 2, and negative 2b plus c equals 8. If I multiply the top equation through by a negative 1, just doing basic elimination method, I get a negative b minus c equals negative 2. Negative 2b plus c equals 8. So negative 3b is equal to 6, which means b is negative 2. Now that I know what b is, I can go back to one of those equations. And I'm going to go to the top one. A plus b plus c is 3. A was 1. B was negative 2. So c must be 4. So the bottom line is that 3x squared plus 7x minus 2 over, oh, and there's a part b to this, over this thing factored is equivalent to, now put the a in, 1 over x, put the b in. B was negative 2 over x plus 1, and then c was 4 over x minus 2. So that answers part A. Part B was, now integrate that function. So part B wants us to then put integrals here. I don't want to rewrite it. All the way across the... No, let me not do this. That's the answer to A. B wants us to integrate it, so I'm going to write this. And then 4 integral of 1 over x minus 2. This is a really nice technique because the integral of 1 over x is the natural log of x. The integral of 1 over x plus 2 is the natural log of the absolute value of x plus 2. And then this one is the natural log of the absolute value of x minus 2, plus some constant, and they called it a k in the book this time. I'm just going to keep calling it a c. It's not quite finished yet. We had rules for logarithms that said if you have a number in front of a log, it's really an exponent on the x plus 2 in this case. I'm looking at the second term. So that 2 needs to be an exponent on the x plus 2, and the 4 needs to be exponent on the x minus 2. Now, since those are both going to be even exponents, I can drop the absolute value bars. And I'm going to make an extra step that the book didn't take. Let's see. Natural log of the absolute value of x minus the natural log of x plus 2 squared plus the natural log of x minus 2 to the 4th plus c. So I make one fraction. The absolute value of x goes on top. Anything that's negative belongs on the bottom. The x minus 2 belongs on top, and then there's a plus a constant. So remember the rule that the negative on the, when you put natural logs together, if they're added and subtracted, positives are in the numerator, negatives are in the denominator. So that completes that problem. Now, going back to part A, look back at the original equation where I factored it out. I'm going right back to here where the star is. And here's a cute little trick. Let me just draw a line down here to do this. In the first fraction, actually, I think I'm going to rewrite it. Maybe I can fit it in here. Okay. See if you can follow what I'm saying, because I can't cover stuff up. The fraction that has the a in the numerator, you can't let x be 0. So now you go to the left side of the equation, cover up that x in the denominator, and stick in x is 0, just on the left side. So you're going to have 3 times 0 squared plus 7 times 0 minus 2 over 0 plus 1 times 0 minus 2. If you stick the 0 in all of that except for the x, you get a negative 2 on top, and you get 1 times a negative 2 on the bottom, and so we get 1. Well, take a look at the problem, the very end of the problem. Right here, I'm looking now, about 2 inches higher, a was 1. So now on B, the number underneath that, x plus 1, can't be 0, which means that x can't be a negative 1. So I go over to the left side of the equation, I cover up the x plus 1, and I stick negative 1 into the numerator and denominator, just not into the x plus 1. And when you do that, let's see, we get 3 minus 7, that's negative 4, minus 2, that's negative 6, over negative 1 times negative 3 is 3, and so I get b is negative 2. And that's exactly what we got when we did the problem the first time. Now part C. X cannot be 2. So I go to the left-hand side, cover up the x minus 2 in the denominator, and plug 2 in the rest of that fraction. So 2 squared is 4, times 3 is 12. 12 plus 14 is 26, minus 2 is 24, over 2 times 3 is 6. The answer is 4. So C is 4. So it took us, what, 3 lines to do the A, B, and the C, and then it takes us right to go up that line right there. So it saves a whole lot of paper, but it only works when all of your denominators in your partial fractions are of the linear type. They can't have squares or cubes in them. They have to be linear. And they call it the finger method. It works really well for those kinds of problems. It's going to get a little ugly otherwise. The book also has a shortcut listed in it as well. I don't know that it's any better, but the same idea. So that's number 1.